All right, I'm going to start. Text your friends. Tell them class is starting. Because I think that we're under half. Yeah? Yeah. It's Friday afternoon. Gosh, I wish I could, give you additional benefit for being here. I don't know how to do that.
0.01%.
Free pizza. You don't need extra credit. You're here. Tips on the MP. Draw pictures. All right, let's work. So I don't have a lot new to say, except that I want to, is it too loud? It's like there are so few of us in here. Maybe this is too loud. All right. Let's see. So, I want to revisit stacks for just a second, because there's one thing about my friend here that I forgot to tell you. I think it doesn't surprise you that we can put anything we want into stacks, right? We saw, physically that we could put candy into stacks, and we saw by examples that we can put integers into stacks, and it kind of makes sense that we could put spheres or spaceships or any other kind of user-defined type that we might want to use. But what I think is extra cool about this guy is that each one of these entries is actually intended to be a full pack of Pez, a full pack. So when I look at this device right here and see, oh, it's a stack, what really goes through my mind is it's a stack of stacks. So this is like the golden thing to illustrate the point. Stack of stacks. All right. Did you hear that? Could you hear it? All right. Let's work. Okay. So we had replaced stacks with queues in our contemplation. We're starting to think about queues now. And we talked about the abstract data type for a queue, which includes these two functions for sure. That is a mechanism for inserting data into the structure and a mechanism for removing data from the structure. Pretty much have to have those two things in order to use any kind of structure. And then by convention, we also provide a function called empty that just is designed to give the client the ability to check for emptiness on their own. Okay, so that's the abstract data type itself. We had just begun the question of how should we implement this thing? How should we use memory to implement it? If you do a quick glance at the screen, if you do a quick glance at the slide, your response would be, oh, hey, how about if we use a linked list to do this, right? Okay, now let's check and make sure that the members that we've got make sense for that. For a linked list, we need a queue node or an ability to make a node. We need both an opportunity to enter and an opportunity to leave the structure. That is, a place where we do on queue and a place where we do day queue. Now, because we're implementing this thing with nodes, we're going to use node pointers for each of those things. I've drawn a picture here, and I'm going to give us just, something so that we can communicate about it. What I want to know from you is how we're going to use our linked list in the context of the queue. And the particular question is, which of those handles on the structure, H or T, which of them is entry and which of them is exit? Okay, that's the question of the moment. One of them is going to be the entry, one of them is going to be the exit. I want to know which is which. All right? All right. So what do you think? T is for entry and H is for exit? Or is it the other way around? Is it T is for exit and H is for entry? Okay, raise your hand if the suggested solution is the one that you believe in. You believe that H is for exit and T is for entry. Raise them high. Come on, be brave. Okay? Raise your hand if you think it's the other way around. H is for entry and T is for exit. Okay, about split. The majority of you aren't voting at all. That's okay. I'm kind of pissy today, huh? Sorry. All right, so let's examine these two cases. In particular, let's examine the second case where we use T as the exit. Now think about what we want to do. We want to grab, I'm going to put this in a different color so we can distinguish it. We're going to grab the value 4 and essentially get rid of that node. Well, what does that mean about the exit next time? Where should the exit next time be? Pointing to? Okay, how are we going to get that? Yeah, look at, you got to go all the way back to the start of the list and walk it forward to get to what is the new last element. So, the suggested solution of using the entry at T and the exit at H, even though it's, to me, it's kind of counterintuitive, right? All the arrows are pointing that way, right? All the arrows are pointing the way you think the queue should go. Even though that's true, we set it up like in the suggested manner. Now, just to convince you that this is a good idea, I want to talk about how you do entry to the queue at the end. Now, I assert that you already know how to do this, right? So I'm going to do it pretty schematically and pretty quickly. So here's what you do. You make a new list queue node pointer. What's your favorite number? 5. You put a 5 into it, and maybe you give it a temporary name. Then you assign entry next to it, to that new thing that you just made, and then you increment entry. That's it. 3 simple things, right? Create the new node, fix the pointers, increment entry, and you're done. What is the running time of that? Constant time, right? There was no iteration involved. Okay, fine. Now let's talk about exit at the front. Well, all you do is you grab the next thing, free up this memory, and increment exit. Right? What's the running time of that? Also constant time. When we say constant time in this context, we are pointing out the fact that we're pointing out the fact that we don't care if there are a gazillion things in this queue. There could be millions and millions of things in the queue, and the running time of on queue and day queue would be the same. Okay, are there any questions? Yeah? What are you checking for? Because when you say checking, I'm thinking search. And what we're doing here is just maintaining a sequence of values. There's no search involved. We're just putting things in and taking things out. Or, let's see, putting things in and taking things out of it. We're not ever searching for it. Does that? Why not have a sentinel node is the question. Would that solve the problem? And the answer is a no, because we would still need to set up the place where we do an exit as the one before. And the only way to do that is to start at the beginning and walk forward. Now, there is a reasonable suggestion, and that is, why don't we use a doubly linked list? That would solve the problem. That would solve that problem. But it's good to have to go through this exercise. And in this case, a singly linked list is adequate. We can solve our problem given memory as it is here. Remember that if you use a doubly linked list, you've got an extra pointer for every node. So it's not a lot of memory, but it is a little bit of memory. So, and we've got a solution that doesn't demand that. Okay, any other questions about this? I want to pause for a moment and look at the questions here. Okay, one of the questions is, if you want to remove something from the middle of the queue, then you would have to search. Yep, that's absolutely true. But guess what? If you remove something from the middle of a queue, it's not a queue. Okay? It's a queue with a hole in the middle, which is a perfectly valid kind of structure. Okay? But it isn't a queue in this classic sense. Okay? And we might have to think even more cleverly about how we do it. In fact, I think I would do two queues. I would implement a queue with a hole in the middle as two queues, probably. Let's see, other questions. If you remove the last node, you won't have an entry. I guess that that's a speculation on the answer, because in our case, we arrived at, I hope, an agreement that really, so you will have an entry. It's always at the end. The entry will always happen at the end of the queue. So I'm not sure. All right. I should have brought you a Pez as a treat. Yes, that's true. Sorry. Okay. So let's talk about alternative implementations of this. So here we have an implementation of a queue as a singly linked list. We kind of referred to the fact that we could implement it as a doubly linked list, and I said, no need to, so let's not. What are some other alternatives for implementing a queue? Yeah? Oh, yeah, guess what? In MP4, which I'm not sure you want to talk about yet, but tomorrow would be a good day to talk about it. In MP4, we ask you to implement a queue with two stacks. Yeah, and we ask you to implement the stack with a list, like a list class. So, you know, this conversation about how you implement these things could go on and on and on and on. My next slide, though, our next slide, though, implements the queue as, let's take a look. What do you think? Yeah, simple old dynamic array. Okay. All right, let's make sure we believe that. The private member items, that's the name of the array. The size is the number of data elements contained in the array, and the capacity is the max number of data elements. ELTS. Okay. All right. So let's to get a handle on how we might use this thing, let's go ahead and look at an example. So the top row there is intended to be the array items, and we're going to start by on-queuing 3. I hope that none of us will disagree that right here is a reasonable place for me to put the 3. Is that okay? Yeah, all right. Now, though, I'm going to on-queue an 8. Where would you like me to put the 8? Next to the 3 is right. Should I put it before the 3 or after the 3? It's kind of free for me to put it after the 3. What location is that? I know it's location number 1, but in general, where is it? It's wherever size is, right? And now size is 2, and the place I'm going to enter something is right there. Okay, this is kind of cool. So on Q4, if I'm following what you suggested before, I'm going to put a 4 here, and the next place I'm going to add to the Q is here. Now I'm going to day Q. What gets day Q'd? 3. Okay, good. Do you like this? Do we? Do we have to do that? So here's what's important in your queue. It's important to know what's at each end of it, right? That's really it. The only of the block of data. The only important thing is to know what's at the entry, what's at the exit, and that everything in between has kind of stayed the same order relative to each other. Now, we could shift, but it feels to me like it's unnecessary work because if just by leaving the 8 and the 4 here like this, I've still got a front and an end. Wait, I don't know which way. An entry and an exit. I've still got an entry and an exit position, and all my data is still next to each other. So actually moving it to a new place feels to me like it serves no purpose. Okay? So let's make note of that. What should I keep track of here? What kind of things should I keep track of? To keep track of the entry and the exit locations. What type of thing is it? Yeah? Yeah, they're array indices, right? They're not pointers. I drew them as arrows, but they're not really pointers. So I'm going to use an integer for entry and an integer for exit. And what I want to do next is kind of carry through the example a little bit, okay? So now I want to on Q7, which means a 7 goes here and I increment entry. Then I day Q and day Q. So I return 8, or grab 8 and increment, grab 4 and increment. Okay, so the entry is 1 past the 7 and the exit is the 7. Now I'm going to on Q2, 1, 3. On Q2, on Q1, on Q3. Now I'm going to on Q5. It's getting stressful, isn't it? There and there. Okay, so kind of 1 past, that's fine. So let's keep going. Day Q, I'm going to day Q the 7 and point at the 2. And now I'm going to on Q9. All right. We've got a couple options here. Yeah? Oh, look at that. Look, so when I say on Q9 at this moment, you might go, oh, I learned something new last week, or last time. We could double the array and copy the data, right? And then we would know we would have space, but we haven't used all the space in that array. So all we have to do, I'm going to rewind for just a second, is when we on Q the 5 and make note of the next entry spot, we're essentially going to wrap it around to the front of the array. So we're incrementing entry mod capacity. Okay, so this is incremented mod capacity. And in fact, that's true for exit as well. It's just that none of my examples will get that far. Okay, and now when you see on Q9, you simply do 9 increment entry. Okay, any question about that? Is it okay? All right, so sometimes when you're in conversation about this material with, I don't know, your friends over coffee or something like that, or your aunt that calls to ask how school's going, people may refer to this as a circular array. Okay, so that's sometimes how this is referred to, but it isn't really a circular array. I kind of don't like that explanation because there's nothing that's curving memory around. It's just that you're wise enough to know that that's the effect of taking mod in this context. Okay, let's see. So I want to take this example one step farther and say that, imagine that we've used our Q so that we're in the state that you see on the slide. And in particular, the exit is M and the entry is here. Okay, so we're right here in the illustration. Now I want to on QD, so the entry wraps around, we just learned that. I'm going to put this exit down here. It's easier to see. And then I'm going to on QA, that happens here. Then I'm going to, and we increment entry. Then I'm going to on QY, increment entry. I'm going to on QI, increment entry. This is extremely stressful, isn't it? On QS, increment entry. And then we're going to day Q. No problem. Okay. Okay. But our reprieve is short-lived because now we're going to on QA. H. I have no glasses on, so we're going to on QH, increment entry, and then we're going to on QA. Uh-oh. A comes along, and there's no place to put it. What's the solution? Double the size and copy the data, right? That's what we learned last time. That's how we implement this, thing of unknown size using an array. Using a dynamic array. Okay, how do we copy the data? I've got my data there, and I need to get it into this box. How do I do that? Oh no. Any suggestions? Yeah? DayQ it into the array? Oh, that's a good idea. You can use those functions to do it, right? DayQ everything and on Q it into here. Very good, actually. I'd never thought of it this way. This is cool. The effect of doing that would essentially be to move, let's see, O, N, D, A, Y, I, S, and then there would be room, OH, and then there would be room for the A, okay? Do you all see that? I always would have done that explicitly, iterating from entry to exit, but it's actually much wiser to DayQ it and onQ it into the new space because we have functions that do that work for us already, okay? All right, any questions about this? So what is not done is we don't try to match the shape of it. We don't take the OND and stick it at the end. There's absolutely no reason to do that. We use the new structure as if it's clean. We're starting over. It's a clean queue. Sort of like 8 o'clock every morning for our queue, for the char queue. All right, any other questions about this? Okay, so what's the running time of on queue? Well, let's go through these things and make sure we completely understand them. What's the running time of empty? What does empty do? Just checks the size, right? And so the running time is big O of 1. We could have called this anything we want. As I referred to earlier, this function is one of convention, and you may sometimes see it referred to as is empty, perhaps, but we're calling it empty here. For screen real estate purposes, I try to make things as short as possible. Okay, what's the running time for, let's do day queue first. What's the running time for day queue? I mean, really, it's just incrementing an integer and returning a value, right? So this one has to be big O of 1. Now let's talk about on queue for a second. Usually it's super fast, right? Usually when there's space, it's super fast to on queue. If there's not space, we have to grow the array. Does that bother us? No, we showed last time that on average it makes each individual addition a little bit more, but over the course of the algorithm, it's just a constant time effect per piece of data. So we're going to say big O of 1 on average, and remind ourselves that we have an occasional long wait in resizing. Okay? Any questions about all that? Yeah? Yeah, then the same, yep. If we were doing this carefully and we decided we were shrinking the array upon day queue, then that same qualification for the argument would be the same for day queue as well. So it would be constant time on average. And again, with the explanation that we have this occasional resize downward this time instead of larger. Good point. Okay, let's see. So we're ending, in our virtual textbook, we're ending a chapter, and our next chapter is one that exposes a lie. I said about a week ago that we were completely done with the C++ portion of the course, and it just isn't true. There's one more little thing that is more meaningful after you have the idea of abstract data types and after you have started thinking about the algorithms associated with using data structures. And so I want us to talk about that. The code associated with these new paradigms in C++ is illustrated in the next slide. So here's what I want you to do. I want you to scrutinize this code, see if you can infer what it's doing, and mark beside every line that you think does something kind of new and interesting. Okay, something that you think bears conversation. So spend some time doing this. Okay. So I actually did want to say something about that very first line that I put an asterisk about. So it was a bit of a ruse when we talked about the list ADT as if it was this new magical thing. The standard template library in C++ actually gives you a list class that you can use. We didn't need to re-implement it. And this is how you refer to that class. It also affords random access. I believe that you have the first thing and the second thing, and it might even start at 0. I'm not sure. So it's a different interface, and I suggest that you go look at it and use it if you think it ever becomes useful to you. It's certainly the substance of our discussion today. There's a little comment later about how we insert into it. Okay, now what I'm going to do is I'm going to walk my pen down the screen, and I want you to tell me to stop when you see something that you think would be interesting to discuss. Okay, so going for a walk, it's a beautiful Friday. You have to yell at me. Okay, you want to stop here? Oh yeah, that's a good one. So that's a member function of the animal class. I mean struct. Struct, I mean, oh, they're the same. Okay. That's a member function of the animal class. Is it public or private? Public by default. And if you had to describe what that function was, you would say it's a constructor. Very good. So that's a constructor of the animal class. Good job. All right. So the use of the initialization line there, name, food, and big, putting the values in, that should not be a surprise to you. You've seen that before. There's nothing mysterious about it. Would anybody like to speculate on the sort of elephant in the room when we talk about this? Yeah? Yeah, so this is a way that we can set default values to parameters. And yes, you can use this in any function that you like. I think that's true. I say it so affirmatively, and then I'm like, wait, I never checked that out. But I see no reason why you shouldn't be able to use this in any function that you like. But what it's getting for us here is some constructors for free. So take a look a few lines down. When we actually declare some of those animals, when we declare some things of animal type, look, all of a sudden we've got a 2-argument constructor. It initializes an animal that's a giraffe that eats leaves and it's big, right? We also get a 3-argument constructor, which seems a little more obvious. We also get B, which is a big bear that eats you, right? So the question is, how is this working? And we can speculate on that by instead asking the question, how many constructors do we get for this? So what I want to ask is, how many constructors do you think we get via that one function definition there, via that one constructor definition? How many do you think we get? Yeah? It looks like we should get 8, right? It looks like we should get 8. Yeah? But we only get, say it again, we only get 4. That's right. It looks like we should get 8 because we want to be able to say X and then nothing for the first one and, zebra for this, wait. Ew, what's an animal that eats zebras? Candy for the second thing. and let it be big, a big blob that eats candy, right? But this doesn't work. We have to honor and use the parameters in order. So the defaults only apply from the right side going left. And in fact, when you design function interfaces, you can have this in mind. You can have it in mind that if you have something for which you want to allow a default value, it goes at the end instead of at the first. Okay? All right, any questions about all that? So the only other constructor that we might deploy in this example is a blob, a z, say. Okay, so we could just declare a z. Like this. And what would we have? What would z be? A big blob that eats you. So like a bear, but a big blob. Okay, any question about that? Okay, so I'm going to erase that because it kind of messes up the example if I keep it. So this is, gives 4 constructors for the price of 1. All right, lecture helper says, stop! I don't know what to do with that. Okay. Would anybody like to add on to that request? A question? Oh, I know what it was. I was holding my pen. Got it. Okay. I got it. Okay. Let's keep going then. Okay. May I go? Tell me I can go. Just kidding. All right. So I'm going to walk my pen down again, and I want you to tell me. Yeah? The indices of what?
Of like the item's constant. So like, how does it know that the last item, or that it's reached the last item?
Because it starts from the front and it instantiates the things from the front. So the minute you stop instantiating parameters to your constructor, it starts applying defaults. Does that make sense? So that's kind of what it's doing. It instantiates while it can, and then the minute it can, it takes defaults the rest of the time. All right, I'm going to keep walking down the screen. So we've already talked about this. I'm going to pause here just for a, I don't know, rest stop. This is how you declare a zoo, which is a list of animals. Okay, so that is a template instantiation of a variable whose name is zoo and whose type is a standard template library list of animals. Okay, let's keep going. Another little pause that is explained by the comment. So we use push back, meaning push to the back. From the list, from the standard template library list class, okay? And that's all documented in C++ reference online, or is a short Google away. And you're going to tell me if you want me to stop. Oh yeah, stop and pitch your tent. Okay, all right. If you smear your eyes, so don't look at the details. Don't look at the details. If you had to describe what you think maybe this for loop is doing, what is it? Yeah, going over the list and printing out the name and food of everything in the list, right? Okay, so let's figure out whether that makes sense. So here's the thing. A for loop normally, what does your for loop usually start with? Yeah, but how does it get 0? Like what do you type right here? Int, right? Int I maybe, right? Or J or K or whatever. Int variable name. So this thing is, oops, too much. This thing right here is a type. We don't quite understand yet what type of thing that it is, but we understand that it's going to play the role of the integer in a normal for loop. So we don't really know what it is, but we know that it's going to play the role of an integer because this still is a for loop. Okay, fine. And then int is the name, or it is the name of that thing. Now, here's another question. What is begin? And I want a word that starts with an M. It is a member function of the list class, right? Because zoo is a list. All right, I've got some, so it's a member function of the list class. We know that to be true because zoo is a list. Now I've got some questions about it for you. Is it public or private? Stereo, I'm getting conflicting stereo, I'm getting harmony here, or dissonance. Is it public or private? It has to be public, right? Because we're using it, and we're a client of the list class. So it must be public in the list class. Here's a harder question. What kind of thing does it return? What is its return type? An iterator, very good. We know it has to be an iterator because the things on opposite sides of that assignment have to be the same. So now look at how much we know, and we still have no idea what an iterator is. An iterator is a type of thing. It's public in the list class because we can use it. It tells us it's in the list class by list animal iterator. So, and it's public because we can use it. Begin is a member function that returns one of these things, and we still have no idea what it is. Well, guess what? We almost don't need to know exactly what it is. We only need to know how to use it. So let's figure that out. Okay, fine. We're going to keep going in our for loop until we reach the end of the list. And look at, here's the increment. We increment it. We increment IT just like we increment any other integer or any other counter that we're using. Okay? Now, though, things get kind of interesting. What does it look like here? A pointer. Wait a minute. We incremented it and we dereferenced it. That feels a little weird already, right? So this is something, the iterator is something that we can both increment and dereference. And the minute we dereference it, which is really not the minute we dereference it in quotes, we have access to the data associated with it. Okay, so dereferencing an iterator returns what type of thing? An animal. That's right. Dereferencing that iterator return to us an animal of which we can ask name, of which we can ask food. Okay? All right. So now I'm going to send you a little bit of ESP and let you, I think I know what your question's going to be. Can I write down 2 more things first? Okay? And you can tell me whether I'm wrong about what your question will be. Okay? All right. So let's look at what this list prints out. If it works like this, or what this for loop prints out, if it works like I'm claiming. It prints out, what was the first one? Giraffe and leaves. Right? And then we increment the iterator, and it prints out penguin and fish. Are we done? Is this your question? No? Okay. So now you really have to wait. Okay. Are we done? Wait a minute. So raise your hand if you think we're done, because the iterator now is at the end. The IT is now at the last thing in the list. The iterator's at the end. Okay, but we're not done, right? Because there's something else left in the list. And yet, look at, we're at the end, like the iterator's at the end. So here's the thing. By convention, that is, everybody agrees, and everybody who ever designs an iterator puts the end one past the last thing. Okay? So the end, this end, is one past the last. Okay, so in fact, we actually do get that last thing, the bear that eats you. Okay? Any question about it? Okay. So I'm actually going to use my last, oh, go ahead and ask your question. I'm sorry. No, it doesn't. So the observation is, well, that iterator is behaving like a pointer. And so there's an attempt to try to figure out, well, what does plus plus of that iterator mean? And I'll tell you right now that we actually don't know how the iterator is implemented. We don't know how that iterator is implemented. We don't know whether it's a pointer or an integer, an array index. We don't know. It's an abstract idea that behaves like this. It can be used to iterate across the data associated with any class that we decide needs an iterator. So if our class is wrapped around an array, we can make an iterator that increments indices. If our class is implemented using linked memory, then our iterator does look more like a pointer. But you know what? An iterator is an abstract thing. Our data, our use of memory, might be a hypercube, right? In which case, if we define a way of getting around it, that is, if we set up a way of navigating it through a for loop, then we can design an iterator for a hypercube class. All we need is an interface for the iterator class that has both increment, dereference, and I'm going to put that in quotes, and all of these other things implemented. We don't need to know how they do it, how it is done. And that's where we'll pick up next time. How is it done?
Unrelated, if I download all the stuff for like the NPs or the labs or something, can I get it to run on like Visual Studio on my...
I have never tried. I
Really?
haven't ever
Okay.
tried on a Windows machine to get it going.
Well, maybe I'll try.
But are you using Windows 10?